Hello, thank you for joining this session. My name is Masayuki Ishikawa from Sony. Today I'm going to talk about running NuttX with MMU, Memory Management Unit, on QEMU. Here, QEMU is an open source processor emulator and we can run NuttX on it. About me, I have several technical backgrounds, including embedded systems. As you can see in this slide, I introduced Linux, Android, and NuttX to our audio products before. Since 2016, I've been joining several conferences such as Embedded Linux conferences and NuttX online workshop and talked about how we applied NuttX to our audio products and also talked about feasibility studies such as SMP and networking. Here is today's agenda. First, I introduce MMU and MPU, which is Memory Management Unit and Memory Protection Unit, and NuttX build types as well as board support history. Then I explain both V7A NuttX and RISC-V NuttX implementations. After that, I will show you how to build NuttX and show you demo video. And finally, I will explain future work. First, let me explain MMU and MPU. Perhaps most of you already know them. As you can see in this slide, MMU means a memory management unit, and its features are virtual memory management as well as memory protection and cache controls. On the other hand, MPU means a memory protection unit for low power processors such as Cortex-M. It does not support virtual address translation, and it supports region-based memory protection only. And also please note that RISC-V MPU is called as PMP, physical memory protection. The feature is almost same as ARM MPU. In NuttX, we have three build types. They are flat, product, and kernel. In this session, I'm going to focus on a kernel build type, but let me explain a flat and product build type as well. And most of you are using the flat build type, which does not use MPU or MMU. Regarding application address space, the kernel build type has a per application-based address space by MMU. In the flat build type, application runs in privileged mode, which means that there is no differences between application code and kernel code. However, in the protected build type and the kernel build type, application runs in unprivileged mode. And also, memory protection can be done by MPU or MMU, respectively. Regarding loadable application support, in the flat build type and protected build type, it is optional. However, it is mandatory for the kernel build type. Finally, task creation API support is slightly different between the build types. In the flat and protected build type, we can use both task create and POSIX spawn MP. However, we can use task create for the kernel build. We cannot use task create for the kernel build type. The next slide shows an example of the flat build type. In this case, user applications are statically linked to the kernel and run in the same address space, which means that applications do not use system calls and are not protected because MPU is not used. As you can see in the linker script and the map file, kernel code, for example, ARM full context restore and application code, for example, knsh main, exist in the same area. In addition, a loadable application is possible, so that is dynamically linked to the kernel. This slide shows an example of a protected build type. In this case, user applications are statically linked to the NuttX user.bin, which is separated from the kernel. Also, applications use system calls and are protected by MPU. As you can see in the linker script and the map file, kernel code and the user code are separate. So please note that loadable applications is also possible. However, the applications are dynamically linked to NuttX user bin, which is not the NuttX kernel. The final one is the example of a kernel build type. As I explained earlier, this type uses MMU, and user applications run in their own address space. As you can see in the memory map figure, the init application and the hello application use the same virtual addresses. However, they are mapped to different physical pages by MMU. So this model is similar to Unix environment. Next slide shows ELF support differences between the build types. In the flat build type, undefined symbols such as printf in the hello application are resolved at runtime. In this case, symbol tables exist in the N shell in NuttX.bin, and application calls rv-virt symbols directly. In the protected build type, undefined symbols are resolved at runtime. This is the same as flat build type, but symbol table exists in the N shell, which is linked to NuttX user.bin, which is separate from NuttX kernel. And rv-virt in the NuttX user.bin uses system call here. In the kernel build type, rv-virt is statically linked to applications because currently shared libraries is not implemented. In this case, undefined symbols are not permitted. And also in this case, system calls are used, so which is the same as protect build type. This slide shows support history on config build kernel. The config build kernel was introduced by Greg in around 2014. However, the build type has not been maintained in a long time. And this year, I ported this kernel build type to server 6 quad, which has Cortex A9, but I only tested with a single processor configuration. After that, Oki-san added SMB support to them. As for RISC-V support, we ported to our iSQL board, and Then I ported the rv-virt environment, so which is based on QEMU. So before talking about MMU, we need to understand CPU mode. In ARM-v7A architecture, there are many processor modes. In ARM-v7A NuttX, we are using user and IRQ and supervisor and the system mode. If a processor mode is in a user mode, it runs in unprivileged mode. In this mode, some instructions cannot be used. In the CPSR, this is a current program status register, there is a mode bit field, and you can find the current CPU mode in the CPU register. So, and like this. This slide shows more concrete examples for ARM-v7A NuttX CPU mode. When the CPU starts with the reset handler, the CPU is in SBC mode, supervisor mode. This SBC mode also happens at the entry and exit of the SBC handler. In these handlers, we change the CPU mode to the system mode immediately. And when hardware interrupt happens, CPU change to IRQ mode and jump to the IRQ handlers. In the IRQ handler, we switch to system mode immediately. The system mode is used for kernel code, including kernel set. For example, idle task or HP work, so which is used for networking. And user mode is used for user tasks, as well as the pthread and signal handlers. So you can see here CPS registers like this in a GDB. The next slide shows an address translation for ARM-v7A. With MMU, we need to use page tables to map virtual addresses to physical addresses. In ARM-v7A architecture, two-level page tables are used for address translation. ARM-v7A defines a supersection that supports a 16 megabyte memory region for the first level. However, in ARM-v7A NuttX, we only use 1 megabyte memory region for first level table. Similarly, we only use 4 kilobyte memory page for the second level, even though ARM-v7A supports 64 kilobyte memory page. Here, the first level table has 4096 entries, which means that the table size is 16 kilobytes. And the second level table has 256 entries, which means that total table size is 1 kilobyte. After setting up tables, we need to set TTBR, translation table-based register. The next slide shows a memory map for Sublet 6 quad KNL. The Sublet 6 quad support board uses NXP's i.MX6 processor, which has OC RAM, on-chip RAM, as well as SE RAM that locates following physical addresses. Regarding virtual addresses, I assigned addresses as follows. In the kernel area, there is there are an L1 page table and kernel text data heap and page pool, whose addresses are the same as our physical address. Regarding a user text data heap, which are allocated from page pool, like this, and map to a different page memory with MMU. When ARM-v7a NuttX boots, the start function in rv-virt is called. This is a common logic for ARM-v7a NuttX. In this function, the L1 page table is initialized here, and finally set on TTBR here, translation table base and register. As I explained in the previous slide, L1 page table exists on the ARM i.mx6 OCRAM. As I explained, there is the page pool in the SDRAM. This is a memory pool used for L2 page tables and L2 pages for user text data heap, and a granular allocator is used to manage the pool. Regarding the page pool API, there are the following APIs. And for example, when loading a ELF file, for example, MMPG is called to allocate pages for text data heap for it. Here, please note that on v7 NuttX, the L1 page table is statically allocated, and the table will be updated instead of updating TTBR when switching a context. The next slide shows the kernel heap and stack. In NXStat, up allocate kheap is called to allocate the heap. In this case, in the case of sublet 6 quad KN shell, the heap exists between G idle stack, so which is at the end of the kernel data area, and PG heap, like this. To initialize the heap, KMM initialize is called. In the kernel code, kernel memory is allocated with KMM alloc. The kernel stack is allocated with up address and kstack alloc, and stored to TCB XCB kstack. After that, switch to the kernel stack during system calls in ARM syscall.c. The next slide shows the user heap and stack. The user heap is initialized with UMM initialize when user application starts. The heap's address and the size are configurable in defconfig, so like this. The user stack is allocated from the user heap and then stored to TCB stack alloc PTR, which is same as flat build type. As you can see, the user heap address user heap area can be seen in the core stack, like this. The next slide shows struct task group S, which is allocated when creating a task. The struct holds such as child exit status, environment variables, file descriptors, file streams, sockets, and address environment for MMU, so which is very important for the kernel build type. And please note that if a task creates a pthread, the thread will belong to the struct of the current task. The next slide shows a struct group addresses, which is a CPU architecture specific struct. In the rv-virt NuttX, the struct retains MMU information for task group. More specifically, it holds L1 page table entries for the user app's text data and heap. And there are some APIs for the struct. For example, app address and creates address environment when loading a user application. In this API, it calls app address and create to allocate physical pages with MMPG alloc. Another example is app address and select, which selects address environment when switching a context. Regarding context switching in NuttX, there are some APIs associated with it. For example, when application calls read system call for the UART driver, then the driver calls NXSM wait and wait for user inputs. In this case, app block task is called from NXSM wait, and it calls switch context to issue SBC instruction, supervisor call instruction. And when a user input happens, do IRQ is called, and then calls a group address env to change the address environment associated with the task. In rv-virt NuttX, the L1 page table is statically allocated. Because of this, app address env select does not change TTBL, but only updates the L1 page table entries for user apps. This means that the kernel address space mapping is not changed. Also, please note that RISC-V NuttX implementation is different, which I will explain later. This slide shows the core stack for starting the init tasks. In Server 6 quad KN shell, it uses the hostfs, host file system, to mount system/bin, then call exec spawn. As you can see from this core stack, the kernel code is running to load the init task. This slide shows core stacks for starting hello app from the init, so which is known as nshell. In this case, nshell calls project spawn to load the hello app. As you can see from these addresses in the core stack, the user code is running. From here, I explain about RISC-V NuttX implementation. In the RISC-V specification, there are some MMU modes defined, such as SB32 for RB32 architecture, and SB39, SB48, and SB57 for RB64 architecture. However, in RISC-V NuttX, currently only SB39 is implemented. To work with MMU, RISC-V needs to use S mode, supervisor mode, to run the kernel code. However, we need to use M mode, the machine mode, as well to access such as mtimer, mHeart ID, so on. In RISC-V, we need to use eCore, environmental core, to change the CPU mode and jump to exception handler to proceed. This is a big difference between RISC-V and ARM. To access a for example, mtimer register from S mode, so we need to use, for example, OpenSBI, so which is open source supervisor binary interface, or we need self-implementation for QEMU RB. As I explained in the previous slide, NuttX implements SB39 mode. This mode uses 3 level page tables that are L1, L2, L3. Each table has 12 entries, and each table size is 4 KB because entry is 64 bits. For example, L1 entry maps 1 GB, and L2 entry maps 2 MB, and L3 entry maps 4 KB respectively. RISC-V has SATP, supervisor address translation and protection register, to specify L1 page table. The next slide shows a memory map for rv-virt knsh configuration. This configuration uses 8 MB RAM, but the size is configurable. Also, virtual address for PG4 and the user text data heap are configurable in defconfig. The address mapping is almost same as sublet 6 squad, but it does not use a dedicated L1 page table. In RISC-V NuttX, page tables for the kernel mappings are statically allocated in the kernel data area. Here, this implementation is different from ARM v7a NuttX implementation. The tables are configured in QEMU rv kernel mapping in initialization. Because the tables are statically allocated, MMPG alloc is not used for the table. And when creating a user task, copy this kernel mapping to the user task in app address and create. The next slide shows struct group address and S for RISC-V NuttX implementation. This struct is architecture specific and different from v7a NuttX. In the struct, there is a member called SPG tables here. In the case of SB39, 2 page tables are allocated with MMPG alloc. SPG table 0 holds kernel and user L1 mappings, and SPG table 1 holds user L2 mappings. And when creating a user application, app address and create is called. In RISC-V NuttX, this API calls copy kernel mapping to copy PGT L1 to SPG table 0. for the kernel area mappings. Then call map SPG table to associate SPG table 1 to SPG table 0, and finally allocate memory for user text data heap from PG table, a page pool with MMPG alloc. And when switching context, app address emp select is called. In RISC-V NuttX, it just restores SATP, supervisor address translation and protection register, with SPG table 0 in the address emp. It's very simple. This slide shows how to build the NuttX kernel with applications for subrest 6-core knsh NSP, which is used in the later demo. First, we need to configure and build the kernel, and by executing configure.shell, sh, and make. This step is same for flat build type. Then export the libraries and header files by executing make export. Finally, you can find NuttX and NuttX export the version number /z under the NuttX directory. After that, execute mkimport.sh to import the library and the header files, and then make applications by executing make export. Finally, you can find applications under the bin directory, like this. Before starting the demo video, let me explain the demo scenarios. In the demo video, I will demonstrate the NuttX SMP kernel on QEMU 6.2. The kernel is configured to use ARM Cortex-A9 4 cores with MMU, and total CPU usage can be seen with the top command on the host OS, so like this. In the demo video, I execute several nshell commands as well as applications. The configuration also supports networking. In the demo video, you can see the Telnet daemon and the IPAR are working. So let's start demo video. So first start a QEMU and see CPU usage with top command like this. And you can see a Cyber 6 core configuration is running. So help and PS. So 4 cores are running, and free page table page memories can be seen, and host FS is used, and also we can use networking and how application is running. And SMP, this is application to test a merge core. Okay, so 4 core is currently running. And get prime, this is only one thread is running, and then 2 cores are running. Please see here, 2 cores are running, and get prime 4 runs 4 threads, so 4 core is running, and get prime 5, this is also 4 cores running, but takes more time to finish. Then login with Telnet, and you can see Cyber 6 core, and also you can see a Telnet is running, and yes, SMP application also can run, and run IPAR in server mode, and then run IPAR client on host processor, and you can see almost 100 Mbps can achieve. And you can also run several commands on a serial console. And if you run a SMP command, this will take use a poor processor, so the performance will be degraded, slow down, but soon recover to after finish SMP application. So now iParf application is not running. Yes, PS, and so finally exit telnet daemon. So finally, let me explain the future work for the build kernel. I think the biggest one is we need to improve stability issues, because sometimes a kernel crash happens with data abort. Perhaps there's something wrong with context switching. Regarding RISC-V, as I explained, OpenSPI support is needed for QEMU configuration to work with emp timer. Currently, QEMU works with MMU, which does not I didn't demonstrate today, but emp timer does not work. So also, SB32 should be supported for rv-virt architecture. Other CPU architectures such as ARM64 and x86-64 might be desired. And new features such as shared library and paging would be useful to improve memory usage on NuttX. That's all for my presentation. Thank you.